Hello again, everyone. This is Mr. V. Hill, and today we're going to be talking about arithmetic versus geometric sequences. And we're just going to look at a couple of examples. We've already looked at these, the first two examples anyways, before. The first one that we looked at was this one, 2, 5, 8, 11, 14. And we saw that we got this sequence by starting with 2, and then we always add 3 to get to the next term. So the recursive rule for this, or RR for short for recursive rule, was that we're going to start with 2, or we're just going to say that a sub 0, the 0th term in the sequence, is 2, and then we get to any given term in the sequence, a sub n, by taking the previous term, a sub n minus 1, and then adding 3 to that. And in the last video, we showed how to get the general rule from the recursive rule. So if you forgot this, please go back and watch that again, or look over your notes. And the general rule for this one was that a sub n was equal to 3n plus 2. So this repeated adding 3, remember repeated addition is a multiplication. That's what becomes this multiplication right here on 3n. And this is actually what we call an arithmetic sequence. And just for a goof, let's look at what this looks like if we were to graph it. And this is pretty easy to do. If we were to make a table of values, right, we would have n and a sub n here. You go 0, 1, 2, 3, 4. And you go a sub n is 2, 5, 8, 11, 14. We can actually put this table into a calculator, and a lot of you have probably seen these calculators before. This is the graphing calculator. We do this by just going to the statistics menu, and we'll go over this in class too, so you get a little more practice with it. But we put in this first list the n values. Those are independent variable, really. So 0, 1, 2, 3, 4. And then in the second list, we're going to put the a sub n's, the actual terms of the sequence. 2, 5, 8, 11, 14. Of course, that would continue. Just so we make sure we get to see all of it, I'm going to change up my window here a little bit. Let me go up to at least 15. Oops, that's on x's I need to go from 0 to 5. Let's go from 0 up to 15 here. And we want to turn this guy on. And so when we graph this, oh, wouldn't you know it, there we go. Here are the actual data points that we have in our table. Notice, and this is now in a coordinate plane where the independent variable is along the bottom. Those are your n's. And the dependent variable is on the vertical axis. Those are your a sub n's. So this would be the point 0, 2, 1, 5, 2, 8, 3, 11, and 4, 14. Now, this is the sequence, but notice the sequence is actually a function defined on either the natural numbers or the whole numbers, just on these integer values. And so what would happen if we were to fill in between our data points? Well, we just look at our general rule over here, and notice the a sub n's, well, those are your dependent variable. The n, that's your independent variable. Normally in algebra, what we're doing, we use x and y's, right? Where the y is always the dependent variable and the x is the independent variable. So we could rewrite this equation as y is equal to 3 times x plus 2. And those are the variables we're normally going to be using, x and y, because we're generally going to be using the real numbers here in Algebra 1. So if we were to type this function here into our calculator, this equation, y is equal to 3 times x plus 2. We graph that thing, and it fills in between the data points. And what you might notice here is that this graph right here is a perfectly straight line. And so within Algebra 1, what we normally call these things when we switch over to x's and let x be any real number and not do these n's, which are just going from 0, 1, 2, 3, 4, just these whole number values, then we call this thing a linear function. And that's one of the types of functions that we're going to be studying in Algebra 1, is the linear functions. And they're called linear because, hey, look, it's a straight line, hence linear. Crazy, right? Okay, well, that's the first type, the arithmetic sequences, which are also called linear functions. Let's look at a second example here. This is the one we saw last time as well. 2, 6, 18, 54, 162. Again, the recursive rule we got by starting with 2. So a sub 0 is 2. But then we got to the next term in the sequence always by taking the previous term. So a sub n is equal to the previous one, a sub n minus 1, but we multiplied by 3. And we went through the whole process, and we got the general rule from that to be that a sub n was equal to 2 times 3 to the power of n. And let's take a look at what this looks like if we were to plot it in a coordinate plane. So let's change up these values here. So we're starting with 2 again, but then we go to 6, 18, 54, then 162. Okay, so there was our table. And we're going to have to change the window up so we can see everything. So my x's are fine, but my y's are going to have to go from 0 up to, let's go with about 180, just to make sure we see everything. Don't need to tick mark every single time. And I don't want to see that guy, but I do want to see the stat. So here we go. There are our individual data points. But notice here, this is definitely not a straight line. There's curvature to this. Okay. But the whole point here is, if we were to switch this up, and this is what we call a geometric sequence. When you're multiplying by the same thing over and over again, it's called a geometric sequence. But if we switch these up and call this y and this x, y is equal to 2 times 3 to the power of x. What we would see, here we put that in as well, graph that, and we see this nice curve going through each and every one of our data points. That's wonderful. And so this big steep curve as it shoots off this way, this is called an exponential function. We call it an exponential function because, well, the independent variable is in the exponent, hence exponential. And so the linears and the exponentials, those are two of the types of functions that we're going to be studying this year. That's why we kind of introduced them with a little bit simpler version of them with these sequences. And that's just the basic difference between them. If you're adding the same thing all the time, it's called a linear function or an arithmetic sequence. If you're multiplying by the same thing over and over again, it makes this nice curve, and it is called an exponential function or a geometric sequence. Now we've got one more type of function that we're going to be looking at in this class, and it comes out of sequences that look a little something like this. 2, 8, 18, 32, 50. This is just an example of one of them. But we might ask ourselves, well, let's see here. If this were an arithmetic sequence, we would be adding the same thing each time. So we'd need to add 6 to 2 to get to 8. But would adding 6 to 8 get us to 18? No. So we can't be adding the same thing each time. If it were a geometric sequence, we'd be multiplying by the same thing each time. So 2 times 4 equals 8. But 8 times 4 is most definitely not 18. So, what in the world is going on with this? And this I'm going to kind of leave as an exercise to you guys. So the exercise here is you're going to try to write a recursive rule for this sequence. And if you can, I mean, you might not be able to get the recursive rule. It's a little bit weird. You got to do something a little bit tricky with it. Or you could try to write a general rule for this sequence. Just give it a shot. Try some stuff out. You might notice something about these numbers, and that'll help you. I'm not going to give it away right now, but take some time and play with these things. Again, numbers and all mathematical things really are nothing more than mental Legos. In order to understand them better, you have to play with them. So, give these a shot. Don't kick yourself if you can't do it. That's fine. But play with it a little bit and give it a try. And we'll talk about this a whole bunch come tomorrow in class, or well, whenever you're meeting in class, depending on when you're watching this video. So, give those a shot, and I'll see you then.